Welcome, Regents students. Today we begin a new topic, optics. Now before I begin with the topic, I just want to remind you that you should have printed out some protractors at this point. Obviously, if we were in school, I would provide protractors. But since we're stuck at home, we'll have to do our best. And so what I did is I just went and Googled printable protractor. But you can use the file that I included in the classroom stream. And what I did is I printed the same protractor out, but at different sizes. And for me, what I did to achieve that is I just copied and pasted the image into Word or any word processor. And then I shrunk it down smaller and smaller. And the reason why I now have a whole fleet of protractors so that I can pick the size that's most convenient to use in a particular problem. So it is a little bit, actually, it's kind of a pain. We have to print these out, but it gives us an advantage. Now we have a whole little fleet of protractors, even this little cute one right here, protractor. All right, so on with the topic. You should have also watched the videos of the phenomenon of reflection before this video, because that's what we'll be studying today. In optics, where the two things in this unit we're going to be learning about are reflection, which you already know, the definition of that from the waves unit, and refraction. So you should have seen the light ray reflecting in the short video before. To see how reflection works, now you obviously have used mirrors before looking at your image, but now we're going to look at it in a more scientific manner where we actually measure what's happening with the light as it's reflecting. So the other thing I want to point out before I jump into today's information is, as I mentioned already, we studied in the waves unit that light is a wave. It's a transverse wave. A transverse wave of vibrating electric and magnetic fields. That wave therefore has crests and it has troughs, right? And those are moving through space. And also light can travel through space, which is why we see the sun come up every day. The sunlight reaches the earth through the vacuum of space. Sound cannot, right? Sound can't go through the vacuum of space because sound is vibrating atoms. So light can go through vacuum, but it obviously can go through other things like windows, which are made of glass. It can go through water, oil, so many other substances, not all, but it can go through certain substances. So that's just a few pointers about the optics unit, what light is. And then the other thing we're going to start with today is this concept of a light ray. So light, as I said, made of crests and troughs, as you can see in this diagram, and those crests and troughs are moving. Now, if in class I would take out a little laser pointer and you could see the light ray shining at a laser pointer, and maybe that laser pointer makes red light like a lot of lasers. So these crests and troughs are moving, but we define something called the light ray. It doesn't really exist. It's in our minds. It's a little imaginary thing that allows us to then figure out how light behaves and write equations for the properties of what light does. So the ray, as you can see from this diagram, is 90 degrees to all the crests, the wave fronts that are moving through space. So we imagine that it's actually a line that goes like this. And for the most part in this unit, we could then forget about the fact that light is made of crests and troughs. We just analyze what's happening to the ray of light. All right, so now in this new video system I'm using, the Ed Puzzle, there'll be a little pause right here. And so I'll put these pauses in to give you an opportunity to copy these notes down into your notebook, which you should be doing. So here's the first pause. Okay, so now light, what it does, one of the things that it does is when it encounters a smooth surface, it reflects according to the law of reflection. So here, maybe I'm shining a laser at a smooth surface here. I should have written that down. Well, I could put it in here. This is a smooth surface. And that can be obviously like a mirror made of glass, very smooth when you rub your hand over it, but it could also be any polished metal, okay, or other things like a smooth water on a still day. So any kind of smooth surface. If I shine a laser coming down like this, it bounces off the smooth surface or the mirror. This ray coming in, we call it the incident ray. Okay, so that's what's written here. And then it bounces off, we call that the reflected ray. Okay. Now, it doesn't bounce off at some random pattern. If we draw this imaginary line called a normal, which is perpendicular to the smooth surface, we can measure with a protractor the angle of incidence, the angle from the normal over. We call that theta incident. Then we measure the angle from the normal over to the reflected ray right here. If we do that for a smooth surface, we would find that those two angles are equal. That is the law of reflection. The simplest formula you can have, one thing equals the other. But in optics, like for example, if I take my little protractor and I measure this to be over from the normal, 10, 20, 30, about 35 degrees here. That's the incident angle and the reflected angle. The angles are not measured to the surface. So if this is 35, then this is obviously 55 because they add up to 90. So the theta incident is not 55 degrees. It's 35, reflected 35. It doesn't matter so much for the law of reflection because if we said 55 equals 55 or 35 equals 35, then we would be saying the same thing. But later when we learn about refraction, it's absolutely critical to measure the angles properly to the normal. And even in this if they ask. So again, a pause in the video so you could copy this section down. Okay, moving on. Light doesn't always reflect in this very regular pattern according to the law of reflection, because most of the time when light hits surfaces like this paper, the wood behind it, okay, or your clothing or your skin or the roadway, those surfaces are not smooth. Now you might say, oh, this paper seems pretty smooth to me. If we had a microscope and we blew up the surface of the paper, we might find it's jagged with all the little wood fibers and all the things that make up the paper. Okay? So we would see on a microscopic level, this paper is not smooth, even though on a macroscopic level, when we look at it here, it does look smooth. If we shine laser light like this with these pink rays showing the light coming in, what happens is because the surface is not smooth, the different rays here, you see this reflects with the law of reflection goes up this way. But the second beam comes in here and look where it's hitting here. It's hitting a surface like that which reflects it that way. So these two rays are not parallel anymore. And same with the other two. So when you hit a rough surface with light, then what you see is diffuse reflection. The light sort of spreads out in all directions. If I were to take, in class I do this, I have a mirror here and I shine a laser down and then it bounces off and the light goes that way, then you would see if the mirror was perfectly smooth, you would not see any laser light hitting this point because 100% of the laser light would be going off in this direction and none straight at the camera. But if I shine the laser light at the piece of paper, now some of that light doesn't go like this and reflect. It reflects straight at the camera. So you would see a red dot here if the laser was red and the light came in like this, and look, it bounces straight up at 0 degrees to the normal. This came in maybe 60 degrees to the normal. And so the law on a macroscopic level does not hold. Okay, so theta incident does not equal theta reflected on the macroscopic level. Light gets scattered when you shine it on a rough surface. All right, the next thing we're going to be doing, so here's another pause in the video so you could copy this. Okay, the next thing that we're going to be doing is that we will be constructing reflected rays. This is something that you have to do in the Regents. Okay, so I have here the start, a light comes down like this, okay? And we have to be able to construct the reflected ray. So this is how we're going to do it. Let's see. Yeah, this is a pretty good protractor out of these three, right? I'm going to pick the one that matches the problem perfectly, you know, as big as I can without completely covering everything. So what I do is I put my protractor like this. See how it hits right here? So maybe I'll put a little mark over here so we can see that. So it hit there, so I put this bottom of the protractor here, and then I align this with the bottom of the protractor with the surface. So you see here lined up. And then what I do is I put a little dot for the normal, and I'll construct the normal later. And then what I do is I count, protractor move. I count how many degrees over. Now I say this all the time. You should ignore the numbers on the protractor. This says 90 degrees. It's not 90. Well, you can't see it, but I could see it. It's not 90. It's 0 degrees because we measure all the angles from the normal. And this is the normal. So this line is on the normal, 0 degrees from the normal. This is 10 degrees away. It says 80, but we ignore the numbers. So the incident angles 10, 20, 25, 26, 27. Yeah, looks like about 28 degrees. Okay? So I'll jot that down, 28 degrees. So what I have to do to make the reflected ray is I've got to make 28 degrees on the other side. Again, ignore the numbers. See, 90, 100, 110. No, this is 10, 20, 25, 28 is somewhere around there. So I make a little mark and I remove the protractor. Now what I do is I take a straight edge and I put it down to construct the normal, and I could use a dotted line, I suppose. And then I take the straight edge and I make the reflected ray, which will go like this. And I would label that reflected ray. On the Regents, they like these little labels, and I could even put theta reflected here. Theta reflected equals 28 degrees. Okay? So another pause to the video, but I'll say this, that when you draw this, use a straight edge, your angle might not come out to 28 degrees, and that's okay. Maybe when you draw some arbitrary line coming into the paper, it comes out to be 35 or something like that. If that's the case, just make it bounce at 35. Make it accurate to the law of reflection over here. Okay, so again, a pause to give you some time to copy. All right, the next thing we're going to do is see how we could create an image in a mirror. Because obviously when you look at yourself in the mirror, you see an exact replica of yourself. If your hair is standing out on its end in the morning, on top of your head, in the mirror it is too. Okay? You wear a red shirt, you're wearing a red shirt in the mirror. So what's in the mirror is an exact replica. But we humans understand that there really isn't an identical twin of us in the mirror when we look at it. We understand that that's an illusion created, that there's an illusion of an identical twin in the mirror. But how does that happen? Somehow our brains see whatever's in the room, they see an exact copy in the mirror. What we're going to do is see how that happens here with a little ray tracing diagram. So I put a coin in front of a mirror here. And obviously we see a coin, another one in the mirror. If we were not smart enough to realize it's a mirror, we would try and reach in like some animals do that. A bird will look at an image of itself in a mirror, it'll think it's another bird. We understand it's not, but still we see it. So how does that happen? All right, so what we can do is we have to trace two rays. Really what's happening to this coin is an infinite number of light rays are coming off of it. We shine light from the light fixture and then the light scatters every direction. And out of all those rays, some of them go in our eyes. I'm going to just pick arbitrarily two rays. So here's the first one. Comes in, hits right there. That ray, when it hits the mirror, will reflect. let's see, is this a good size protractor? Yes, it is. Okay, so I'm going to now reflect that ray off the mirror. So I make a mark for the normal. A little hard to see off at this angle. And I measure this angle. This angle is 10, well, I see that 15. I'm going to say about 13 degrees. So 10 is right here. 13 is right around here. Okay, so there's my mark for my normal and my reflected ray. So I make my normal. Okay. And then I make my reflected ray. Like so. And you could pause this as you're going along and creating this in your own notebook, and just, so you follow along at this point, draw your best you can. Now, again, maybe your incident ray wasn't 13 degrees, maybe it was 17 degrees. Whatever it is, make that same angle. Here I have 13 degrees, and here I'm going to have 13 degrees. Oops, 13 degrees. But you do whatever angle it came out for you. And then I'm going to take any other ray. People say, what kind of ray should I make? I don't care. As long as it's not this one. Just pick another one, like off over this direction. Okay? I'm just arbitrarily making a second ray. Again, the coin is sending out infinite light rays. So I take my protractor and I'm going to apply the law of reflection at that point. So the light ray came in here, targeted, hit the mirror here, and this is the normal. And what I'm going to do is count over 10, 20, 30, looks like 39 degrees. So 39 this way reflects 39 this way. 10, 20, 30, 9 degrees. Okay, so there we go. I got my normal and my reflected ray. So let's now fill those in. There's the normal, and the reflected ray will be like this. Oops, a little bit off. All right, well, it'll be a little off. See, I missed the mark. By the way, there's a lot of drawing in this topic, as you can already see. And that means that your answers very often will be off a little bit. That's okay. The Regents will allot for you to be a little bit off. They'll allow maybe a degree off, or maybe a millimeter off of, when you're drawing and finding the locations of things. So just do your best. Try and be as accurate as you can. If this were the Regents, I'd probably grab my eraser and erase this and try again, because I wouldn't want to be off. But now we're just doing notes. All right, so here, these are two reflected light rays. They go into your eyes. One maybe goes into your right eye and the other one into your left eye. Now, how do you figure out where something is? Like, for example, if there's something on a table like this, and I say pick it up, everyone can go like this and pick it up on the first try. Not many people would be going like this. Not many people would be trying to grab it over here and go like that, right? You would go, first try, grab it. How do you do that? What happens is this sends out light rays that go to each eye, like this. And so this goes into one eye, this goes into the other. And your brain knows that the object is wherever those two lines intersect. And so since you were a baby, clumsily trying to grab things, your mind has become better and better at figuring out and estimating where these lines converge, and then reaching out on the first try and grabbing. So that's how you determine where the location of something is. Same concept over here, but these rays came off the mirror, and what happens is your brain says, I know where the object is. It's wherever these two lines originated from. And so in your mind, it extends those lines. So that's what I'm going to do. I'm going to extend this line back behind the mirror. Okay. Okay. I'm going to extend this line coming from the other, going into the other eye. Again, this is happening in your brain. And I guess I could go a few more dots here. So, you see how these lines intersect right here? Right there, your brain thinks there's another coin. Well, your conscious mind knows it's an illusion, but there's a real coin here that we could grab, and then we're looking at the mirror and there's another coin behind the mirror which is imaginary. Okay, it's created in your mind. So this is the image of the coin. And that's how it works from an optics standpoint with the law of reflection, why we see duplicates of things in a mirror. It's because of the law of reflection and our brain putting those lines, tracing them back to where they intersect and thinking there's an object there. All right, so now the video's done, so I don't need a pause, but hopefully you got this copy down. Regarding the homework, so there's a worksheet that's included in the stream. So you'll see this, and it's two-sided. So this is page 1 of 2. On the other side, well, I guess in the stream it'll be a PDF. So the second page is here. Okay. So what you're going to do in this page is, like, for example, ray A. You're going to trace it till it hits the mirror. And I'm just going to do it sloppy, but you're going to do it nice and neat. Then you're going to apply the law of reflection. You're going to get your protractor. Actually, a bigger size would be good here. And you'd count out the degrees here, make a dot the opposite side, make a normal. And I'm just going sloppy here, but you're going to do it better. And then you're going to go dot, dot, dot. Okay, there's the normal. And then you're going to make the reflected ray like this, right? So, and label it reflected ray. And then measure these angles, and then write down what this is. Maybe it's 55 degrees. I don't know. I didn't measure carefully. But that's what you do for A, B, C, and D. You reflect those rays off the mirror. Okay? And then on the next page, here, you're going to do that coin ray tracing to locate the image of the coin. So again, you got to do this with rulers and a protractor. You're going to go like this, measure the angles, make the reflected ray, do this here, and then reflect it with a protractor, and then trace these back, and then you say, okay, the image is there. And the same thing here, reflect these two off, and then trace them back, and you should see the image of the coin being somewhere around here. So that's the homework, and I'll see you in the next physics video lesson.